The Flame Nebula, located about 1,400 light-years away from Earth, is a hotbed of star formation less than 1 million years old. Within the Flame Nebula, there are objects so small that their cores will never be able to fuse hydrogen like full-fledged stars. Brown dwarfs. Brown dwarfs, often called failed stars, over time become very dim and much cooler than stars. These factors make observing brown dwarfs with most telescopes difficult, if not impossible, even at cosmically short distances from the Sun. When they are very young, however, they are still relatively warmer and brighter and therefore easier to observe, despite the obscuring dense dust and gas that comprises the Flame Nebula in this case. NASA's James Webb Space Telescope can pierce this dense, dusty region and see the faint infrared glow from young brown dwarfs. A team of astronomers used this capability to explore the lowest mass limit of brown dwarfs within the Flame Nebula. The result they found were free-floating objects roughly 2 to 3 times the mass of Jupiter, although they were sensitive down to 0.5 times the mass of Jupiter. The goal of this project was to explore the fundamental low mass limit of the star and brown dwarf formation process. With Webb, we're able to probe the faintest and lowest mass objects. The low mass limit the team sought is set by a process called fragmentation. In this process, large molecular clouds, from which both stars and brown dwarfs are born, break apart into smaller and smaller units, or fragments. Fragmentation is highly dependent on several factors, with the balance between temperature, thermal pressure, and gravity being among the most important. More specifically, as fragments contract under the force of gravity, their cores heat up. If a core is massive enough, it will begin to fuse hydrogen. The outward pressure created by that fusion counteracts gravity, stopping collapse and stabilizing the object, then known as a star. However, fragments whose cores are not compact and hot enough to burn hydrogen continue to contract as long as they radiate away their internal heat. The cooling of these clouds is important because if you have enough internal energy, it will fight that gravity. If the clouds cool efficiently, they collapse and break apart. Fragmentation stops when a fragment becomes opaque enough to reabsorb its own radiation, thereby stopping the cooling and preventing further collapse. Theories placed the lower limit of these fragments anywhere between 1 and 10 Jupiter masses. This study significantly shrinks that range, as Webb's census counted up fragments of different masses within the nebula. As found in many previous studies, as you go to lower masses, you actually get more objects up to about 10 times the mass of Jupiter. In our study with the James Webb Space Telescope, we are sensitive down to 0.5 times the mass of Jupiter, and we are finding significantly fewer and fewer things as you go below 10 times the mass of Jupiter, DeFurio explained. We find fewer 5 Jupiter mass objects than 10 Jupiter mass objects, and we find way fewer 3 Jupiter mass objects than 5 Jupiter mass objects. We don't really find any objects below 2 or 3 Jupiter masses, and we expect to see them if they are there, so we are hypothesizing that this could be the limit itself. Webb, for the first time, has been able to probe up to and beyond that limit. If that limit is real, there really shouldn't be any 1 Jupiter mass objects free floating out in our Milky Way galaxy unless they were formed as planets and then ejected out of a planetary system. Brown dwarfs, given the difficulty of finding them, have a wealth of information to provide, particularly in star formation and planetary research, given their similarities to both stars and planets. NASA's Hubble Space Telescope has been on the hunt for these brown dwarfs for decades. Even though Hubble can't observe the brown dwarfs in the Flame Nebula to as low a mass as Webb can, it was crucial in identifying candidates for further study. This study is an example of how Webb took the baton, decades of Hubble data from the Orion Molecular Cloud Complex, and enabled in-depth research. It's really difficult to do this work looking at brown dwarfs down to even 10 Jupiter masses from the ground, especially in regions like this. And having existing Hubble data over the last 30 years or so allowed us to know that this is a really useful star-forming region to target. We needed to have Webb to be able to study this particular science topic. It's a quantum leap in our capabilities between understanding what was going on from Hubble. Webb is really opening an entirely new realm of possibilities understanding these objects. This team is continuing to study the Flame Nebula, using Webb's spectroscopic tools to further characterize the different objects within its dusty cocoon. There's a big overlap between the things that could be planets and the things that are very, very low mass brown dwarfs, and that's our job in the next 5 years to figure out which is which and why. These results are accepted for publication in the Astrophysical Journal letters.